So, what's up, everybody? Welcome back to another fun and exciting day of proof, set theory, and logic. Today, we're getting back into Chapter 7, an introduction to cardinality. Does anyone still need a note packet, by the way? Anyone? No? No? Yes? Maybe? Okay, cool. So, our first section is all about the cardinality of a set. So you've probably seen cardinality before. It's counting how many things are in it. But cardinality goes further than finite sets. So we kind of started talking about the basic idea of it before. Here's the gist in a nutshell. Watch a kid count something. When they do, they are explicitly constructing an injective function from the set of things they count, or they are counting, to the natural numbers. I.e., they point at the stuff and they go 1, 2, 3, 4, right? They assign each thing in the set a natural number. And as long as they're, not too young, they don't tend to assign multiple things to the same number. You will see like little kids be like 1, 2, 2, right? Like that kind of stuff. But if you're counting properly, you're constructing an injective function from your set to the naturals. So what we want to do here is we don't want to give the naturals any sort of like very important status just inherently, right? We don't want to somehow treat the naturals as if like that's the counting set, even though it kind of is. We will eventually do this, but what we want to come up with is a way to talk about how big our sets relative to each other without having to rely on like this distinct like reference set. That is, we want to talk about how big sets are in terms of the functions between them. This is like a super common theme throughout mathematics, not just in this class, but in pretty much any other part of mathematics, especially if you get to say like linear algebra. You will see a ton of stuff featuring this theme. The theme is effectively that one of the best way to study objects is to study maps between them. That is, instead of looking at the thing itself, look at the ways that you can turn that thing into other things. And if you put some sorts of restrictions on what types of maps between sets you're looking at, for instance, maps that preserve the structure of the thing in some sense, then you're able to gain information about what the thing is like in terms of what maps exist from that thing to other sets, including perhaps itself. So what we're going to do is basically an instance of this. That is, like this counting notion, how big are things, is all about constructing injective functions from a set to the naturals. That's what you do when you count, right? And so to get at the property of how many things are in a set, what you really, like the best way to get at this, the way that you naturally get at this, that kids naturally do it, is by constructing functions from that set to something else. The types of injective functions you can construct from that set to the naturals tells you something about what that set is like. It tells you how many things are in the set, yeah? So this is kind of like a very frequently repeated perspective, which is to get at the structures of an object, or like what an object is like. You look at the structure preserving maps between that object and other objects. Yeah? Okay, kind of cool. You do this all the time, actually, if you think about it. Like if you want to get at like what this class is like in some way, right? You could look at maps from this class to all sorts of different sets that somehow preserve the structure of the class in some way. For instance, if you wanted to look at like what this class is like in terms of like the distribution of the first letter of people's first names, right? You would be looking at, like, the thing that captures this information is the map from students to first letter of first name, right? So it's like a map from students to letters that preserves first letter, part of like the structure of people in the class, right? And so you can get at information about what a thing is like by looking at the possible maps from that thing to other sets. Cool? Kind of a weird thing to think about, like to talk about what something is like by looking at something else, but it's not too crazy in of itself. So here is a little bit of notation and definitions. So I'll even put these up here just for convenience. Or no, I'll put them down here, why not? We've got these in our note packets, but I'll just put them up here to talk about it. So we'll let A and B be two sets. Define the relation. I'll write it as a triple equal, right? Like equal sign with 3 bars, by A triple equal B if there is a bijective function from A to B. Okay. We say A and B are equinumerous if A triple equals B. That is, we'll read this triple equals as is equinumerous with or equinumerous to. Okay. Likewise, we will define one more. Define A as weird less than or equal to B. I'm going to be terrible at drawing this symbol. It looks much better typeset. If to indicate to whatever way you want to say it, that there exists an injective function from A to B. Okay. So a couple of basic kind of notational pieces. Now let's talk about these things. We'll build into a very nice result, which is known as the Cantor-Bernstein-Schroeder theorem, which says that, we'll get there, I'll show you. Or not definition here, theorem. Let's start with the theorem. So this triple equals relation is an equivalence relation. That's our first claim. Okay, so it looks like an equal sign because it, well, acts like an equal sign. Let's show this is true. Let's get used to dealing with this notion of being equinumerous, being able to put things in bijection. What was that? That was interesting. Okay, we just heard a weird sound, people online. So, all right. Proof, let's do it. So what do we need to show? Yep. We must show that this relation is symmetric, reflexive, and transitive. Okay, we'll do each of these separately. So for reflexive, it's really easy. What function verifies that A is equinumerous with A? The identity function, yeah. The function, I'll write it as ID A, from A to A, defined by ID a of x equals x for all x in A, verifies that A is indeed equinumerous, or A and A are equinumerous. Yeah? Do you believe this? Okay. If you believe it, then I will neglect showing that this function is both injective and surjective. It's a particularly easy one to show that it is injective and surjective. Namely, if IdA of x equals IdA of y, well, from its definition, x equals y, right? Injective. Now, pick any x in A. Is there a corresponding x which hits it? Yes, x. Oh, surjective. Okay, great. So that's an easy one. All right, reflexive, totally fine. Symmetric. Symmetric. Okay, what we want to show is that if A and B are equinumerous, then B and A are equinumerous. So suppose A and B are equinumerous. Then there exists a bijection, that is a bijective function, f from A to B. Since f is invertible, we proved this when we were talking about functions a little while ago, that bijective functions are invertible. All right. F inverse is a function from B to A, is a bijection. So B and A are equinumerous whenever A and B are equinumerous. Does that make sense? Okay, cool. So if you have a bijection from A to B, then you also naturally have a bijection from B to A. It's the inverse function. Just flip all of the ordered pairs defining the function. Yeah? Cool. Okay. Hence, symmetry. Great. Okay, now for transitivity, what do? Composition. Exactly right. Okay, so transitivity. Suppose A and B are equinumerous and B and C are equinumerous. Yeah? We will show that A and C are equinumerous. We show, I will jump to the next board now. Ding. We show that A and C are equinumerous. So, to do so, note that there exist bijections F from A to B and G from B to C. We show that G composed with F, which is a function from A to C, is a bijection as well. Do you agree with this? Yeah? Okay. So how are we going to show it's a bijection? Did we? That is a good question. I do not recall if we prove that the composition of bijective functions is bijective. Did we prove that? We definitely have proved that the composition of injectives is injective. Yeah. Oh yeah, I guess we did. Yeah, we did prove those separately. We just didn't do like the full piece together. Yeah. Okay. Yeah. So here, we can even do injectivity relatively straightforward. Yeah? And it's relatively nice. Even better, let's start with surjectivity. Okay, so for surjectivity, let C be an element of big C. Then G composed with F of, well, what are we going to do? What are we going to plug in to get back C? F inverse of G inverse of C. Yeah? Since G composed with F is just G with F inside of it, this is F of F inverse of G inverse of C. So as F inverses just turn into the identity. You get G of G inverse of C. Turns into the identity. Just get C. Yeah? Okay. That is G composed with F of G composed with F of A equals C for A equals F inverse of G inverse of C. Yeah? But these are not preimages. These are genuinely the inverse functions. They're bijections. Cool? Okay. So for every element of C, we have an element of A that gets mapped to it. Cool. What about injectivity? For injectivity, let's suppose that G composed with F of A equals G composed with F of B. That is, G of F of A is G of F of B. Applying the inverse function of G and the inverse function of F, this yields, well, if these things are equal, then I should be able to do G inverse and then do F inverse. And since I'm doing them to the same thing, I should get the same thing out, right? That is, I should get a bouquet of parentheses for you. Yeah? So we just run through and we progressively start to kind of cancel things out. We get F inverse of F of A equals F inverse F of B, since G inverse is the identity, right? Okay, and this just turns into A equals B. Hey, injectivity, right? Boy, howdy, bijections are nice to work with. Yeah? Feeling good about it or bad about it? If we're feeling bad about it, where are we feeling bad about it? Let me know. Or is it too low on the board there? Sorry. No? Cool. All right. So it's an equivalence relation. Well, we might ask now about this other weird relation we've defined. That is, we might want to show that it has some nice properties. So the relation weird less than or equals to is reflexive and transitive. Okay, you want to prove this one? Let's try it. Okay, proof. To show that A is weird less than or equal to A, we construct an injection F from A to A. The identity, ID A from A to A, defined by, well, exactly the same as before. ID A of x is x for all x in A. Satisfies this. That is sufficient, right? If it was a bijection, if you bought that it was a bijection before, then I hope you buy that it's an injection. Yeah? Cool. All right, we talked through the proof of that at least. Does anyone not see that this is an injection? And if not, just fine. Doubt things, that's okay. Doubting it, maybe? Anyone? Okay, fine. All right, so reflexivity, not too bad. For transitivity, suppose that A is weird less than or equal to B, and B is weird less than or equal to C. Then there exist injections F from A to B and G from B to C. Yeah? To show that A is in fact weird less than or equal to C, we show that G composed with F, which is a function from A to C, is injective. Yeah? It's not too bad. To do so, suppose not. Then there exists A and B in A such that G of F of A is equal to G of F of B. Yeah? Now, since G is injective, what does that mean, by the way? If G is injective, that means that if G of x equals G of y, then x equals y, yeah? So G of thing equals G of thing, hence those things are equal. Since G is injective, F of A equals F of B. Since F is injective, A equals B, a contradiction. So G composed with F is an injection, and A is indeed weird less than or equal to C. Agreeable? We didn't really need the contradiction right there. I don't know, winging that proof, but hey, it's fine. You can get rid of the contradiction and just prove it directly, I suppose. But there's nothing that's hurt by adding this guess. What do you think? Make some sense? Cool. So this is like a nice relation here. It's got like a lot of the good properties of the less than or equal to sign. Yeah? All right. Well, a natural kind of question you might want to ask is, hey, is this a good old-fashioned ordering relation that is it anti-symmetric with respect to the equivalence relation equal sign here, triple equals? So, I need to spritz more on here. Can't wait for them to build this new building, hopefully with better whiteboards. I see them with their construction trucks out there every day, and I'm like, all right, put in the whiteboards already, something that actually erases. I don't know how there are whiteboard manufacturers who manufacture whiteboards that erase quite as poorly as some of these ones do. Like, if your business model is making whiteboards and your whiteboards, like, if you're just like absolutely like, how are you still in business, right? I don't know. Maybe I'm criticizing the whiteboard manufacturers wrongly, and someone's going to come up to me after class and be like, hey, man, my dad makes whiteboards. Like, it's a lot harder than you think. But I don't know. I say it's ridiculous. Yeah, look at that. Look at all that mess. That looks ridiculous. All right, whatever. Anyways, you may ask the following. Question. If A is weird less than or equal to B, and B is weird less than or equal to A, is it true that A and B are equinumerous? That is this antisymmetric with respect to this being the equivalence relation? Yeah? Or to put it another way, if you think about, so our normal antisymmetry, by the way, what is the normal antisymmetry for an or for an ordering relation, or for any relation? That is, it says A what? Yeah. And so this isn't exactly the same thing, but if you look at the equivalence classes under these things, that under the relation triple equals is equinumerous with, then we induce exactly the same thing, right? Exactly the same trick. Yeah? So that is, if you can show that weird less than or equal to, in fact, defines a similar relation on the equivalence classes, which it does, since the equivalence classes are sets of functions that can be put in bijection with each other. So if you have an injection from one to another, then hey, just compose with the bijection, and now you've got an injection from anything in its equivalence class. Yeah? Do you agree with that? So then the question basically turns into the standard notion of equals, right? This looks like antisymmetry, except that we're not using the regular old are they the same, right? We're instead using equinumerous. So this is like the version of it that you get without moving to equivalence classes. Does that make sense? So the question is perhaps slightly strangely phrased in the sense that this looks like we're saying antisymmetry, but if you think about the definition of antisymmetry, we're really saying like is exactly the same as opposed to is with respect to that equivalence relation, unless you want to define antisymmetry somehow with respect to an equivalence relation instead of just more generically like that. So this is like it induces an antisymmetry on equivalence classes, if that makes sense. If it doesn't, just neglect it, and there's the question. How about it? All right. So the answer to this turns out to be yes, and is in fact quite a famous theorem. This is known as the Cantor, let me make sure I spell everyone's name right, Bernstein-Schroeder theorem. Now, sometimes people will just say Cantor-Bernstein theorem, since Cantor and Bernstein were the ones who were famous for proving this and popularizing it. Though Schroeder, I believe, if I remember the history of this naming convention, either proved it earlier to less, and people didn't know, or proved it independently around the same time, unaware of Cantor and Bernstein proving it. So there you go. I'll give everyone their credit. Fun. And it says as follows. So it is the answer to this question. That is, if A is weird less than or equal to B, and B is weird less than or equal to A, then A and B are equinumerous. This is actually a harder thing to prove than you might think. And in the next chapter, we will effectively devote our entire time to proving it. It's a longer proof. Proof will be in the next chapter. Okay, so this is actually kind of a crazy and interesting result if you think about it. What does it mean? Well, among other things, let me throw a crazy example to you. So let me put this as another question, and then I'll ask for examples. So question is, what does this mean? Yeah, okay, here. Let me throw you an example. For one, note that the identity is an injection from, say, for instance, the open interval from -1 to 1 to the closed interval from -1 to 1. Yeah? Would you agree with that? Like just send each number there to exactly the same number. No number gets hit twice. Yeah? Okay, it's not a surjection, but it's an injection. Likewise, f of x equals, say, I don't know, x over 2 is an injection from -1, 1 closed to -1, 1 open. So -1, 1 open and -1, 1 closed are equinumerous. Does that seem right? Sort of messes with you a little bit, right? It's like, okay, here's a set. Throw in 2 more points. How many things do you have? Same number of things. What? That's weird. How about that? Okay, what's a bijection between these guys? What the heck? What do you think of that? I've seen some people kind of go like, ah. Okay, here's a weirder one. Let me try this. Further, consider that the identity is an injection from, say, like the naturals to the integers. Yeah? Okay. Can you make an injection from the integers to the naturals? Yeah, totally. Can anyone think of one? What'd you do? Okay, here's like an easy way to do it if you want to think of one. Here, I'll just write it out. And this will kind of show you the process. So here's 0, 1, -1, -2, or +2, 3, -3. Okay, and I'm going to send these guys to just the numbers 1, 2, 3, 4, 5, 6, and so on, right? Okay, let's send 0 to 1. Let's send 1 to 2. Let's send -1 to 3. Let's send 2 to 4. Let's send -2 to 5. Let's send 3 to 6. Let's send -3 to 7, and so on, right? Back and forth, and back and forth, and back and forth, and back and forth. That's not really an injection, is that? That's a really nice one. That's in fact a bijection, isn't it? Yeah? Oh, whoa. There are just as many in the sense of, counting, right? Like putting things in correspondence with each other. positive and negative numbers as there are positive numbers. What? That's pretty neat, huh? Yeah, some people are shaking their heads like, I don't like that one bit. And you would not be alone. When people first started talking about this stuff, lots of people had the response of, that seems wrong. Like, you know? But hey, it's perfectly consistent with what we've talked about. It's perfectly consistent with like the, you know, little kid counting property, right? Like if I want to count the integers, I could go, there's the first one, second one, third one, fourth one, fifth one, sixth one, seventh one. Just counting and counting and counting. And is there any one of them that I don't count if I count like that? No, I'll count all of them. Okay, so as many as there are naturals, right? I've assigned a natural number, a unique natural number to each one. What? Okay, let me throw you, I won't even write the rest of it. Out for that one. Here. Let me throw a harder one to you. And then we'll talk about this open interval one. What about, let me just kind of put this as like a consider kind of game for us. What about, say, the rationals in the naturals? Well, certainly I can inject the naturals into the rationals. Can I inject the rationals into the naturals? You don't think so? There are plenty of rationals that are not naturals, right? Okay. So think of rationals as pairs of integers, right? One on top, one on bottom, yeah? Okay, so you've got like a grid, right? 0, okay, so here's I put entirely more dots than are necessary here. But you get the idea of what I'm drawing, right? I will continue to draw all of the rest of the dots. I'm going to do it. I'm just going to do it. And I've done it. Okay, so hey, here's the idea. Take a rational number a over b and turn it into ab. Do you believe that there's a bijection like this? Yeah? In fact, when we defined the rational numbers, we were like, hey, let's look at pairs and then talk about like equivalence classes or something like that, yeah? Even not talking about equivalence classes, let's just look at it like this, yeah? Ordered pairs. All right, well, we can't have the second one be 0, yeah? So we'll cut out the case when y is equal to 0. That is, we'll just cut out one of these axes, yeah? Okay, so I don't need to care about a bunch of them. That is, I don't need to care about any of these guys, all right? But that doesn't really matter too much. That's just one little line, yeah? Can you come up with some sort of counting scheme where you would go through and count them all out? There's so many of them. Just try one. Think of one. Think of one a little bit. Okay, here, let me show you one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then just go to the next bigger square. Yeah, that is, just go from whoop, 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 and then and then like that, and so on. Yeah? Count them all out. You gonna miss any of them? No. Every one of them just gets hit exactly once. There are exactly as many rational numbers as there are natural numbers. What? What do you think of that? That's not even just an injection. Well, okay, maybe I should actually be a little bit careful right there. If you're treating rational numbers, like if you're looking at all of them, not looking at equivalence classes, which is what we are doing when we talk about the rational numbers usually. But if we're just looking at the ordered pairs, there's a bijection. If you believe that there is a bijection just looking at the ordered pairs, looking at equivalence classes, there are only fewer things you have to think about, right? If there's an injection or if there's a bijection with an even, the elements making up the equivalence classes, then there is certainly one with just the equivalence classes, yeah? Just don't count the ones in an equivalence class that you've already gotten to, yeah? Oh, what the heck? Does anyone feel like this is weird? A little bit, yeah. What do you got? Oh, okay, yeah, just raise your hand and say it's weird. It is weird, I agree. It is a little bit strange, huh? You else come up with any other ways of counting it, right? There's like a ton of other ones, right? You go backwards on the square, so you could do part of one square, then do the larger one, and then do like the next part, then the next larger one. There's like a ton of them, yeah? Take any bijection from the naturals to themselves and compose it. Bam, you got another one. Easy. What? Super weird. Okay. Fun. Now, there are other fun kinds of consequences of this, quite a few. But let's return to these guys. What's a bijection between the open interval -1 to 1 and the closed interval from -1 to 1? Can you think of any? Weird. Yeah? What are you going to do? It feels like one of them is the other with just two more things, and so you're kind of like out of luck, but it's not true. Let me show you a bijection. And we'll see. I may go through and painstakingly show that this is in fact a bijection. The full details of part of it are in your textbook that are a lot of annoying cases. But here, I'll show you a trick here. So here's the idea. So, oh, I put my good marker down. Where did I put it? Yes, there we go. Good and squeaky. So to show that there is a bijection between -1, 1 and closed interval of -1 to 1. We construct one. Let's make one. What do you think it's going to look like? If your answer is messy, you're right. So here, I'll show you. We'll take h, the function from the open interval, to -1, 1. Let's let this be the function. Ooh, I'll say h of x is -2 to the minus n minus 1 if x is equal to 2 to the minus n for some n in the naturals, 2 to the minus n minus 1, minus 2 to the minus n minus 1, if x is equal to -2 to the minus n for some n in the naturals, and x otherwise. Huh. Okay. So this function, do you believe that it hits everything? Does it hit 1 and -1? Yeah, it does. Observe, h of what equals 1? So yeah, so it would be 2 to the 1 minus 1, 2 to the 0. Yeah? 2 to the 0 is 1. Yeah? And so that would be when n is 1. So that would be 2 to the minus 1. 1/2. Yeah? Okay, so we hit the endpoints. Yeah? If, I'll write it this way, if y in -1 to 1 minus 2 to the minus n minus 1, or minus 2, or 2 to the minus n minus 1, or minus 2 to the minus n minus 1. Yeah? Then there is certainly an x such that h of x is equal to that y. What it is very clear. It's exactly from the construction. Yeah? Does that make sense? Okay. So all of the numbers in this interval of either this form or this form get hit by something. What is the only other possibility left? Well, that there's something in there that's not of that form. But if it's not of that form, h sends it to itself. Oh, it's certainly a surjection, isn't it? Yeah? Oh, h is surjective. Does that make sense? It feels like it's too easy, yeah? It feels like you're like, what? It barely did anything, yeah? All you did is basically said, hey, look, the interval from -1 to 1. It either has numbers that are of this form, or some other form, yeah? If it's of this form, there's a thing that hits it. If it's of this form, there's a thing that hits it. We tell you what they are in the definition of the function. If it's not of that form, there's also something that hits it itself. We have shown that the only two things that belong to -1, 1 that do not belong to the open interval from -1 to 1 are certainly hit by things of this form. Yeah? So we got surjectivity. Injectivity, you should be a little bit careful around. We could go, okay, suppose h of x equals h of y. Well, then we go through our cases. We could say, well, if x is of this form, then this says that this thing is equal to, well, whatever, h of y. And then you go like, well, if y is of that form, then hey, look, they're equal. And then you go through case by case. There's kind of a lot of different cases there, eh? In this case, it's very easy, yeah? But otherwise, everything, you just have to go through the cases. We're out of time, so I won't do it right now. That clock is still very off. Always confusing me. But if you want to see the case-by-case one, check out your textbook. It's right in there. And I'll see you next time. Have a great Friday and a wonderful weekend.